Hi, I'm Colton Miles.
I'm Christopher Bakke,
I'm Aiden Delplanque.
and this is the group If It Ain't Broke and our project on steganography.
Steganography is the practice of concealing a set of data within a set of data. In our case, we are concealing simple black and white images within a colored cover image. Our task was to simultaneously embed 10 of these images and be able to recover them without interference between the hidden images. A cornerstone of steganography is the inability to detect the hidden image within the cover images without specifically knowing the encryption method. One method that we used to embed images was odd and even numbers. Because the images we were trying to hide are black and white, we were able to turn them into an array of ones and zeros based on the relative distance from 0 and 255. Using the mod function, we created a logical array that showed where the odd and even values between the hidden image and either the red, green, or blue channels of the cover image didn't match. We then added this logical array to the cover image layer. The fact that the cover image pixels are on a scale of 0 to 255 prevented the addition of logical arrays from distorting the cover image. This method was practical and allowed us to store up to 3 images on each layer in the cover image. However, because there is no way of keeping track of the changes made to the cover image, we were not able to continuously add images to a layer, as the previous data would be lost.
The second bit method was the second function used to encode hidden images into the cover image. The cover image is an array of unsigned 8-bit integers. The value of each bit is described as a 2 to the n function starting with n equals 0 and increasing right to left across the bit locations. In comparison to the whole integer numbers, unsigned 8-bit integers allow for modification of all 8 bits. Because the values of the bits increase as they move left, the 4 rightmost bits were chosen to replace because they represent smaller values and therefore have a lesser impact on the appearance of the image. In order to embed the hidden images into the cover image, the least significant bit function determines via user input which image will be embedded and the bit location where the embedding will take place. Because each image is flattened at the beginning of the function, it is now made up of an array of zeros and ones. Using bitset, the cover image's 8-bit values are replaced with the hidden image array values, storing the information while causing no visual change. In order to recover the hidden image, bitget is used to extract the array data from the user's specified bit location, which is then expanded and displayed in the GUI. This method allowed us to encode 4 images per layer.
We'll walk through how to use the GUI. First step is loading our images. Using the GUI, we can load our cover image and our image that we're going to mask. First, we'll walk through using the odd-even embedding methods. Using these embed methods on the lower right, we can embed an image into the red, green, and blue channels with these buttons respectively. We can then recover the images by using the buttons on the left-hand side. If we recover the image from the red channel, we recover this image. Well, if we use the green channel, we recover that image. However, the odd-even embedding method only allows for a few options as far as embedding our 10 images into the single cover image. Now, we'll walk through using the least bit method for embedding and recovering images. First, we'll load our next subimage. Then we'll select which layer we want to replace. When we select the least bit embedding method, we have to enter the bit location 1 to 4 we want to use to embed. Let's use 1 for this example. We've successfully embedded that into the cover image. Now we can put this hidden image into the 4th bit of the blue channel, like so. We can now save the image. Now we can load that same image that we saved and recover our secret agent checklist method, or secret agent checklist picture, the least bit blue recovery method. And there you have it, how we use the image encoder decoder. Now we'll walk through how the code handles the encoding and decoding methods for both the odd-even and least significant bit encoding and decoding functions. We'll look at the red channel functions for all of these. This is our GUI function for the odd-even red layer encoding method. First, a variable is set that determines the channel that we'll encode the image into. Then, we call the odd-even encoding function with the cover image, the hidden image, and the channel we wish to encode. Once we get to the odd-even function, we flatten the image, we make sure to pull the specific channel that we want, we make the logical index using the mod command, then we simply match to make sure that the image has the same odd-even configuration as the hidden image that we want to encode. Then we bring the cover image back and only replace the values in that specific layer with the ones that we just modified to encode the hidden image. Finally, we return this to our function, which then updates the handle. To recover, we use a very similar method. We simply define the hidden image using the return function of the odd-even decoding function. All the odd-even decoding function has to do is take the mod of the cover image and expand that to be a full RGB image and recover the image using that method. Coding and decoding functions for the least significant bit method are a little more complicated. Not only do we define the channel we're using by the button we press, but we also have to prompt the user for the bit location we wish to embed. After prompting the user, we then make sure that the user entered a valid bit number. Once we've determined that the user has entered a valid bit number, we'll go to our least significant bit function, which has been passed the cover image, the hidden image to embed, the channel we're embedding, which is red, green, or blue, and the bit number between 1 and 4. We flatten our hidden image to turn it into a ones and zeros image. Then we make sure to pull the layer that we're using, red, green, or blue. Then we simply set the bit we're looking at to equal our binary data that we've already established by flattening the image. Then we return the cover image with only that channel modified. Again, the least significant bit decoding function works in much the same way. Only this time it simply grabs the bit that we're asking for and returns that binary image and expands it into a full RGB image.
And that concludes our project on steganography. We hope you enjoyed it. Thank you!